And that is in yellow, which nobody can see. Okay, today is the 13th of December, 2017. So let's actually do CH2O together. How many of you have it on your paper? Are you looking at it right now? You should be looking at it either on your paper or on Doceri. Do you have something that looks like this? C, double bonded to O, single bonded to two H's, with 1, 2, 3, 4 unshared electrons. Now, a few notes about appearance on these things. Now, you need to have the math to back this up. Why? It gets complicated here's the thing. The math provides a lot of certainty. So to do the math to back this up, we look first for valence electrons. How many valence does carbon come in with? How many valence does carbon come in with? 4. How many valence does hydrogen come in with? You can just vote with fingers. 1. Single. How many valence does oxygen come in with? 6. We have 1 carbon, we have 2 hydrogen, we have 1 oxygen, 4, 2, 6. We have 12 valence electrons. Okay. If everybody was fully satisfied in terms of octet, how many electrons would everybody... Well, how many does carbon want? 8. This is the one that you have to watch. How many does hydrogen want? 2. It doesn't want 8. It can't handle 8. Oxygen wants 8. So times 1, times 2, times 1. 8, 4, 8. 20 valence. I'm sorry, 20 octet. Jeez Louise Moser. 20 octet electrons. 20 octet electrons. So how do we figure out how many are shared? How many they want minus how many they got. So 20 octet minus 12 valence means 8 must be shared. If 8 are shared, divide that by 2. That says there are going to be 4 bonds. That's how we know there's a double bond. We can go on to figure out how many unshared there should be. So if we say that they had 12 valence coming in and they're sharing 8, how many of those valence aren't going to be shared? 4 of them. We got 4 unshared. Figuring out where to put the 4 unshared is where it becomes really helpful to think back to what that atom looked like when it came in, to think back to its initial Lewis dot diagram. And if we think back to oxygen, well, we also count. Before we put those unshareds in, 2, 2, 2, 4, 6, 8. Carbon satisfied, hydrogen satisfied. Without these unshared pairs, whoops, meant to get them both, didn't get them both. 2, 4. Would oxygen be satisfied? No. 1, 2, 3, 4. So now, if we count the octet for oxygen, we have 2, 4, 6, 8. Okay. And if we think back to how oxygen looked coming in, it had 2 paired electrons. The question was, how do we find valence electrons in the D block? The D block is really weird, and the same rules do not apply. In the D block, and we're going to actually talk about that this morning, well, or tomorrow morning, we'll see. In the D block, what happens is because you have that crossover between the S and the Ds and the S's can both act as valence, though it's often the Ds, so we get variable numbers of things that act like valence electrons. So a lot of those things don't form a definite ion, they form multiple different ions. So you can have iron 2, iron 3, and next chapter you're going to learn and love all of those. By the end of chapter 7, you'll know the most common metallic ions, but we haven't talked about that. There is no simple one-size-fits-all for that. Good question. We can do carbon tetrachloride. This is also called carbon tet. Used to be used in dry cleaning fluid. Used to also be used to clean draftsmen's instruments to get the graphite off the instruments. Also a known now carcinogen and teratogen. And when I was in college, we used it in our kill jars in entomology. So you had a mason jar with a couple inches of plaster in the bottom, and you would soak that plaster with carbon tetrachloride. And when you caught an insect that you were ready to kill, you'd throw it in, slap the lid on, and the joke was, don't breathe deep. The insect would twitch a few times and then die. Great stuff. They don't use it anymore. But that's carbon tet. So let's do a Lewis structure for carbon tetrachloride. Where do you start? With the math, because I want to see the math. Once you're awesome at these and you can do them in your sleep, then do them in your sleep. But for right now, I want to see the math. I have something that looks like that. And these are fairly straightforward, these things that are carbon tetra anything. Carbon tetrafluoride, carbon tetrachloride. We did methane, I think, as an example, which is CH4, carbon tetrahydride. And those are really easy, carbon bonds 4 ways. So we'll get into more complicated cases, but having, getting the hang of having the math to back it up while they're still really easy is nice. It is a nice thing. Yes, sir? So there's carbon monoxide, and if we do valence, carbon comes in with 4, oxygen comes in with 6, we have 10. Octet, carbon, oxygen, each one 8. We have 16. So 10 valence, 16 for octet. Octet minus valence, 16 minus 10, means you have 6 shared. How many bonds is that? 3. Now, this is interesting because you've only got one place to put bonds. What does that mean you're looking at? Triple bond. Yeah. So, is it different than everything else? Well, not than everything else that has a triple bond.
I was told that carbon had an extra electron.
Ah, good question. So let's look at how many. I know what they're thinking. Okay, let's look at how many unshared we're going to have. So we have 6 shared, and we have 10 valence. How many are unshared? 4. So where could we possibly put those? This is a good question. Right now, each of those atoms feels like it's surrounded by 6 valence electrons. How many do each of them want to feel surrounded by? 8. So if we did this and said, oh, well, oxygen's got the 2 pairs it showed up with, what's wrong with this picture? Because that's not correct. How many does carbon feel surrounded by? 6. How many does oxygen feel surrounded by? No. 2, 4, 6, 8, 10. That doesn't work. So what we see, whoops, is that carbon has an unshared pair, oxygen has an unshared pair. So not different than everything else. But yeah, you've got, excuse me, you have to distribute your unshared pairs.
Wouldn't it require an ionic bond on top of the covalent bond? Because carbon has 5 starting electrons connected to it.
No, it has 4 valence electrons starting off.
But it has 3 connected to oxygen and 2 on the other side.
2, 4, 6, 8.
I mean, it has 5, like it has 2 over there and 3 over there connected to oxygen. So that would be 5 instead of 4.
You're thinking of the individual electrons. You want to think about the pairs. So if we look at the pairs that carbon feels surrounded by, and I'm going to circle those in red. 2, 4, 6, 8. So are you concerned because of the fact that they're on opposite sides and it looks funky?
I'm just confused on, I don't know how to explain that.
Okay.
I was looking at, like you said, the individual electrons. But now carbon had 5 connected to it, and oxygen is...
No, it doesn't have 5 connected to it. Okay, I see what you're saying. It's still got 4 sites of attachment. So carbon basically forms 4 bonds. We haven't talked about orbital hybridization yet, which is what allows carbon to form 4 bonds. We're going to talk about that. That comes at the end of this chapter. So in essence, whoops. In essence, this is, it will not let me draw that. This is one thing attached to carbon. It's one orbital. How many electrons can an orbital hold? 2. That is one thing attached to carbon. These 2 electrons are one thing attached to carbon. These 2 electrons are one thing attached to carbon. These 2 electrons are one thing attached to carbon. So this is where we start to think of those electrons in terms of pairs. And we count pairs. So 2, 4, 6, 8, and carbon's satisfied. Does that help? Okay. Good question. And when we look at oxygen, we see the same thing. 2, 4, 6, 8. We've got 8, the feeling of 8 electrons around it. Now, does either carbon or oxygen have full ownership of all 8 of those electrons? No. And, you know, is this bond going to have, is it going to be polar? I don't know, I'd have to do the math. I suspect so, because carbon is carbon is not all that electronegative, and oxygen is fairly electronegative, despite how close they are on the periodic table. So I would certainly guess that if we had the tools to do it, we would find that oxygen was pulling more of the electron cloud towards it. But at this level of writing Lewis structures, we don't care. At this level of writing Lewis structures, we're concerned with making sure everybody's meeting octet in the octet conformers, and we don't go into the deeper stuff yet. So, does that work? Okay, cool. So you already know that ionic compounds are made up of positive and negative ions combined so that they cancel out and they're neutral. Okay. So we could take our old friend, sodium chloride. Sodium has a what charge as an ion? What's the charge on sodium? What's the charge on sodium? Fingers. Just hold up a finger. What's the charge on sodium? 1. Plus or minus? You got your periodic table out, right? Plus or minus? Yeah, it's cation. You're good? No? Okay, so that's one where you probably need to stop in after school. We should work on that. So sodium's going to give up 1 electron to be like
To get to this.
that noble gas. So it's going to give up 1 electron. It's going to have 1 more proton than electron. So sodium is 1 plus. Chloride, group 17. What's the charge on chloride ions? 1. Positive or negative? Negative. It's gained an electron. It's got 1 more electron than proton. It's going to be negative. I see some furrowed brows. When we have a chunk of sodium chloride, like this, giant chunk of halite, chunk of sodium chloride, or the smaller crystals that come in that tube for 49 cents at Aldi's. All it is a bunch of these all jammed together in repeating patterns, and I'm going to do these repeating patterns right here, in a sort of a crystal lattice. And what we get is something that ends up, and mine is going to be uneven because of the limitations of my drawing here. But we get what ends up looking like this huge network of positive and negative charges. Now I chose sodium chloride because the geometry is a little bit easier, because they're all 1 charges. So for every one sodium ion, we have one chloride ion. And they line up so that the sodiums are next to chlorides and the chlorides are next to sodiums. And then we get these forces of attraction running in all directions through the material. Now, the cool part is that gives them some very special characteristics. Special characteristics indeed. And I'm going to go ahead, let's see, let's paste a few more of those. If you're drawing this on paper, I can tell you that you'll have to repeat it again and again. So most ionic compounds tend to exist as crystalline solids. What the heck does that mean? Well, we're going to try to grow crystals later this year. And what it means is that they have a definite repeating structure. That's all it means. So this has a definite repeating structure. Any other ionic compound is going to have a definite repeating structure based on how those ions are arranged next to one another. Okay, well, what does that do for them? A couple things. Well, it makes it so that their formulas are not like the molecular formulas we've been dealing with, where it actually means that there are 2 hydrogens and 1 carbon and 1 oxygen. It means it's just a ratio. So I'm going to borrow this whole thing. Well, let's see. Can I borrow this whole thing? Come on. Copy. So when I borrow that whole thing, when I look at that whole big chunk, can I count the number of sodiums in here? Can I count the number of chlorides in here? No. All I can do is establish a ratio based on their charges. That's all I can do. Because I can't count. So I can't say this is sodium. I mean, God, what would it be? Sodium 4,736,542? Who knows? How big a chunk are we talking about? So ionic formulas are different than molecular formulas in that regard. For sodium and chloride, Na1 plus, Cl1 minus, the formula is NaCl. Did you do crisscross in physical science? Do you remember crisscrossing? We're going to do a lot of it next chapter, but how did I get the subscripts there? What are the subscripts here? They're ones. If it's a 1, we don't write it. We take the magnitude of the charge, bring it down and over, magnitude of the charge, bring it down and over. That gives us our ratio. Let's do one that isn't beautiful. Let's do magnesium chloride. What's the charge on magnesium? Fingers, number of fingers. 2. Positive or negative? Positive. So magnesium is going to be 2 plus. Chloride, well, we already did that. 1 minus. To figure out the ratio, we're just going to bring the magnitude of that down here. Magnitude of that down here. Now, if the subscript is a 1, we actually don't write it. The fact that we have the element there tells us that there's at least one of it. So we do not write 1s in subscripts, so this would be written as just MgCl2. It's really important to understand that this is not the same as a molecular formula. We're not saying there's 1 magnesium ion and 2 chloride ions. We're saying that for every 1 magnesium ion, there are 2 chloride. It's a ratio. So it's a little bit different. Okay, now here's the cool part. Lewis dot diagrams have not abandoned us for ionic compounds. Remember that you can draw a Lewis structure for, and we're going to use fluorine because it's an easy example. So we can draw a Lewis structure for a neutral fluorine atom. Okay, so we have this neutral fluoride ion. What does fluoride want to do regarding electrons? Gain or lose? Gain 1. Could we show this with an extra electron? Yeah, why not? So I'm going to copy this so that we preserve both images. When we show something having gained an electron, and I just color-coded it to mentally make it obvious to us that that's the one it picked up, it now has a full complement, and it also has a charge. And whenever we show something with a charge, we have to put it in brackets. And we have to put the charge outside the brackets. That's going to become really important when we start doing polyatomic ions. So we can show the fact that fluorine has a 1+ charge. Can we show, let's do sodium fluoride. And I'm going to move my neutral fluorine up there. I'll move my fluoride ion up there. Let's show sodium. How many valence electrons does sodium have? 1. So I'm going to put a single dot there. What does it want to do? Give up or gain? Give up. It's going to give up that 1. So we can show now Na 1+. Could we show an ionic compound this way? They're not sharing electrons. We can't draw lines between them. Remember how we express this? Everybody stand up. Stand up, stand up, stand up. How would you show that with these Lewis structures? I'm going to copy this. I'm going to paste it. I'm going to copy that. I'm going to paste it. Hey, look at that. They're shoulder to shoulder. They're not overlapping in any way, shape, or form, but they sure are a compound. So we can actually show ionic compounds using Lewis dot diagrams. I don't expect you to be able to explain lattice energy well. I want you to understand that lattice energy is what's associated with ionic compounds. Okay? It's sort of the equivalent of bond energy for ionic compounds. And it's the amount of energy, it's the difference in energy between a mole of gaseous ions and a mole of the solid. Okay? So it's technically the energy released when we go from a mole of the solid to a mole of the gas. But it's just a little different. Now, I said that there are forces of attraction extending in all these directions. Every one of those sodiums is attracted to every single one of those chlorines near it. But what's also true? Would there be any forces of repulsion in there? Can you identify a force of repulsion that you would see? What do you think? Yeah. Well, chlorine is repelled by other chlorines, and actually sodium is repelled by other sodiums. So we have this sort of balance of energy, similar to the bond energy, but these are much more extensive. These aren't just between one atom and the adjacent atom. These are between every single ion in the whole chunk. What does that do for us? Let me get rid of my little arrows, and I'll show you. Let me copy this whole big chunk of salt. Copy. Paste. So when we have a molecular compound, like sugar, C to C to C to C to C, 1, 2, 3, 4, 2, 3, 4, 5, 6, with some adjacent hydrogens, and I'm probably not going to draw all the hydrogens, and some hydroxyl groups. The bonds inside that chunk of sugar are really strong. So every carbon and hydrogen and oxygen, they're holding hands. They're sharing electrons. I left a chlorine behind. Whoops. So every one of these atoms, I'm totally getting the numbers of hydrogens and oxygens wrong. You'll have to forgive me. Gesundheit. Within this molecule, it's hard to break up. You need a lot of energy to break up that molecule. But between two of these molecules, you can get them to move apart pretty easily. There are not a whole lot of forces of attraction between the molecules. So I can put a bunch of these molecules of sugar together, and I can heat them up, and I can get them to start sliding past one another. What do we call it when we heat something up and the little pieces of it start sliding past one another, becoming all liquidy? What do we call it? Have you ever done this? Oh, wait. Hold on. Oh, just dry them up on your pants. In molecular compounds, it doesn't take that much energy to break the bonds between the molecules and get them to move past one another. To melt it. In the lab, when you had 3 molecular and 3 ionic compounds, well, whoops, I gave that part away, but that's okay. Did you have some things that melted at much lower temperatures? Yeah. Based on the research you did with your textbook, did you suspect that those were perhaps molecular compounds? You can melt sugar on a stovetop at home. Try it with salt. You'll actually probably melt the pot first. No kidding. Salt takes a lot of heat. Salt, table salt, is an ionic compound. To break that into a liquid, you got to add enough energy to overcome the forces of attraction between every single sodium and every single chloride in that whole giant chunk. You're not going to do that with a candle in the lab. It's just not going to work. So ionic compounds tend to have very high melting points, much higher than molecular compounds. The other interesting thing about them, the other thing is that when you drop a chunk of salt in water, and let me expand my chunk of salt here a little bit, it'll make it easier to see. Water is polar. It has regions of partial charge. It snakes its way in between all these things, and it breaks them up really effectively. And what you end up left with is a bunch of ions in solution, a bunch of charged particles in solution. When you have charged particles in solution, you got something that will conduct electricity. We call it an electrolytic solution. So ionic compounds tend to conduct water when they're dissolved. Looking at the conductivity test video that you viewed, did the ones that had high melting points tend to be the ones that conducted, with one exception? Okay. They were. There was one exception, which is citric acid. Citric acid conducts because it's an acid. We'll talk about that in chapter 15. That comes down the road, why that happens. Those are electrolytic solutions. Okay, any questions on any of the stuff we've talked about today? Any questions about, okay, because I don't care about dodgeball. I honestly do not.